Hello, we are starting chapter 4, module 1. In this module, we will study connectedness. What is connectedness? In elementary real analysis, we have already studied a theorem called intermediate value theorem. Intermediate value theorem says that if f is a continuous function from R to R, and if we take the restriction of f on an interval, then it assumes between any value between any two image. Connectedness is a property of an arbitrary topological space which has generated from the intermediate value theorem of elementary reanalysis. Let us consider some known topological spaces, for example R, for example set of rational number, for example R minus 0, or Euclidean spaces, or Panchart plane, and say RL, that is R with the lower limit topology. What our intuition says, which topological spaces between them will be connected and which will be not connected. Our intuition says that R with usual topology is not possible to make any disconnection within R. So, it will be connected. It is our intuition. But this does not happen in case of Q, the set of rational numbers. For example, if we consider the set of all rational numbers less than root 2, and if we consider the set of all rational numbers greater than root 2, then it makes a disconnection of Q. If we consider set of all negative real numbers and set of all positive real numbers, then it make a separation of the set of R minus 0. Now, if we go to R square or any Euclidean space, our intuition says that there will be no disconnection. Now, what about RL? We need some workable definition of connectedness or disconnectedness to say whether RL is connected or disconnected. So, let us go to slide presentation. As we have discussed, in this chapter we treat a topological property that will be of central importance in the study of manifolds, which are most important topological spaces. The definition of connectedness is formulated so that connected spaces will behave similarly to the intervals in the real line. So, for example, a continuous real valued function on a connected spaces satisfies the intermediate value theorem. So, let us formulate the formal definition of connected topological spaces. A topological space X is said to be disconnected if there exists a separation of X, that means a pair of non-empty disjoint open sets U and V such that X is equal to U union V. X is said to be connected if it is not disconnected. So, that means we can say that a topological space is disconnected if we can separate it by two non-empty disjoint open sets, which automatically means that a space is disconnected if it can be separated by two non-empty disjoint closed sets. By this definition, connectedness is a property of a space, not a property of subsets like openness or closeness. We can also talk about connected subsets of a topological space, by which we always mean connected in the subspace topology. In this context, we can also consider a separation of A to be a pair of non-empty disjoint open subsets UV of X whose intersection with A are non-empty and whose union contains A. This is equivalent to the original definition because the open subsets of A are exactly the open subsets of X intersected with A. Let us give some example of disconnected spaces. Let us consider R minus 0. In fact, minus infinity to 0 and 0 to infinity, that means set of all negative real numbers and set of all positive real numbers, makes a separation of R minus 0. If we consider the set of all rational numbers with the subspace topology induced from the usual topology of the real line, then for any irrational number, if we take all rational number less than that irrational number and take all rational numbers greater than that irrational number, then we get a separation of Q. So, Q becomes disconnected topological space. Similarly, we can say that set of irrational numbers is also disconnected topological spaces. Now, let us present an example in R2. Let us consider a subset of R2 be the set of points with rational coordinates. Then, if we consider these two sets, that is all xy such that x less than pi and all xy such that x greater than pi, then these two sets give a separation of A. Let us give a question whether R2 minus Q2 in the subspace topology of R2 is disconnected or connected. We shall answer this question after some preparation. To produce example of some connected topological spaces, again we need some preparation. It is intuitively clear that open and closed unit disks, the circle, the whole plane and the x-axis are all connected, at least in the everyday sense of the word. Proving it, however, is not so easy because we have to show that it is impossible to find a separation. But very soon we will come up with an easy technique for proving connectedness that will work in all possible examples. Here is a useful alternative characterization of connectedness which we shall prove in the next page, that a topological space is disconnected if and only if it contains a clopin set. Proof. Suppose first that X is connected topological space and assume that U subset of X is clopin, that is both open and closed. Then V is equal to X minus U is also clopin. If both U and V were non-empty, then U and V would be a separation of X. Therefore, either V is empty, which means that U is X, or U is empty. Conversely, if X is disconnected, then we can write X is equal to U union V, where U and V are non-empty disjoint open sets. This means that V is the complement of U, that is U is open and as well as closed sets. The following is an alternative equivalent condition for connectedness. Proposition: a space X is connected if and only if there does not exist any continuous function from X to the two-pointing set 0, 1. First, assume that if possible there exists a continuous function f from X to the two-pointing set 0, 1. Since both singleton 0 and singleton set 1 are open set in the two-pointing space 0, 1, then F inverse 0 and F inverse 1 form a separation of X. That means if such a function exists, then X becomes disconnected. Conversely, let X be disconnected. Then by definition we can write X is equal to U union V, where U and V are non-empty disjoint open sets. Now if we set a function f from X to 0, 1 as f is equal to 0 on U and f is equal to 1 on V, then f becomes continuous function. In fact, open sets of the two-pointing space 0, 1 are whole space, empty set, singleton set 0 and singleton set 1. So, F inverse whole space is equal to X, F inverse singleton set 0 is equal to U, F inverse singleton set 1 is equal to V, F inverse empty set is equal to empty set. That means F pullbacks each open set to open set. This means that F is a continuous function. Hence, we can say that if X is disconnected, then there exists a continuous function from X to 0, 1, this two-pointing set. The following result will be extremely helpful to prove that product of connected space is connected. So, proposition: let X be a topological space and B alpha be any collection of connected subspaces with a one point in common, then union of B alpha is connected. Proof: let B alpha be a collection of connected subspaces of a space X, and let singleton set P is contained in the intersection of B alpha, alpha belongs to A, where A is the index set. Now we shall prove that union of B alpha, alpha belongs to A, is connected. To prove that it is connected, we have to prove that it has no disconnection. So, if possible, there exists a disconnection. That means there exist non-empty disjoint open sets C and D of X such that Y is contained in C union D, and both of C intersection Y and C intersection D are non-empty. The point P is in one of the sets C or D. Without loss of generality, let us consider P belongs to C. Now, since each B alpha is connected, it must lie entirely in C or entirely in D, and it cannot lie in D because it contains the point P of C. Hence, each B alpha subset of C. So, union of B alpha is contained in C. This proves that union of B alpha is a connected set. So, in the previous theorem, we have proved that a union of connected spaces will be connected if they have a common point. It will be helpful to prove that Cartesian product of connected spaces is connected. For students, it will be better if you first imagine it as R cross R. Let us consider R is connected, which we will prove later. Now, union of say x axis and say y axis will be connected because they have a common point origin, and both x axis and y axis being homeomorphic with R is connected. Similarly, union of x axis and any vertical line is connected. Now, if we take the union of all such crosses, then they have the x axis as common and all such crosses are connected. So, their union will be connected. We shall use just this theme to prove that in arbitrary case product of two connected spaces is connected. So, let us come to the product of connected spaces is connected. Proposition: any product of finitely many connected spaces is connected. Let us consider k many connected topological spaces x1, x2, xk. Now, their Cartesian product x1, Cartesian product x2 up to xk can be written as x1 Cartesian product xk minus 1 and Cartesian product xk. That means it can be expressed as Cartesian product of two spaces. Now, if we can prove that connected spaces, Cartesian product of two connected spaces is connected, then we can say that Cartesian product of k many connected spaces is connected. In fact, by induction we can say that Cartesian product of any finitely many connected spaces is connected. For this, let us choose a point, say x0, y0 belongs to x cross y, where x and y are two connected topological spaces. Then let us consider the set singleton set x0 Cartesian product y. This is homeomorphic with the space y and hence connected. Now, let us choose a point y belongs to capital Y. Then x Cartesian product singleton set y, that is also connected because it is homeomorphic with the topological space x and x is connected. Then union of x Cartesian product y and x0 Cartesian product capital Y is connected because they have a point in common. Let us denote it by AY. Now, if we take union of AY where y belongs to capital Y, then it covers whole x cross y, and x Cartesian product singleton set small y is contained each AY, and therefore x Cartesian product y becomes connected. Now, let us prove another important result. In a space X, closure of a connected space is connected. In fact, we can prove that any set between a connected subset and its closure is connected. For this, let B be a subset of closure of A containing A, where A is a connected set of a topological space X. Suppose B is contained in C union D, where C and D are non-empty disjoint open sets of X. Then this set A must lie entirely in C or in D. Without loss of generality, let A is contained in C. Then closure of A is contained in closure of C. Since C and D are non-empty disjoint open subsets of capital X, therefore C bar and D are disjoint and B cannot intersect D. This contradicts the fact that D is a non-empty subset of B. Therefore, we are able to prove that closure of a connected subset of a topological space is connected. Another proposition, let A subset of X prove that if C is a connected subspace of X that intersect both A and x minus a, then C meets boundary of A, where boundary of any subset of a topological space is the difference between the closure and its interior. We shall prove this by the contradiction method. If C does not intersect the boundary, then in fact C intersection interior of A and C intersection interior of x minus A becomes a separation, which contradicts that C is connected subspace of X, and therefore the proposition holds. Now we shall prove another example which will prove that R2 minus Q2 is connected, assuming that R is connected. Let A be a proper subset of a topological space X and let B be a proper subset of another topological space Y. If X and Y are connected, then X Cartesian product Y minus A Cartesian product B is connected. For any x does not belongs to A, we have Vx is equal to union y belongs to capital Y, xy is contained in M is connected as a set homeomorphic to Y, and for all y does not belongs to B, hy given as this is connected as well. Suppose x does not belongs to A and y does not belongs to B, then C is equal to VA union HB contained in capital M is connected. The two sets have the point AB in common. Moreover, for any x does not belongs to A and y does not belongs to B, Vx and Hy intersect C and M is equal to union of Vx where x does not belongs to A, union of Hy where y does not belongs to B. Therefore, M is connected. We end this module by proving that continuous image of connected spaces is connected, which can be considered as a generalization of intermediate value theorem. Let x, y be two topological spaces and f from x to y be a continuous map. If capital X is connected, then Fx is connected. If possible, let Fx be disconnected. Then there exist disjoint open sets U and V in capital X such that f of x is equal to U union V. Then F inverse U and F inverse V become non-empty disjoint open subsets of X whose union is capital X. That means that capital X is disconnected. This gives us a contradiction. Hence, continuous image of a connected space is connected. With the generalization of intermediate value theorem, that is continuous image of connected space is connected, we end this module. Let us pass to the next module.